Hello my dear students, welcome back to the class. So in our previous class we have learned something about the bar magnet, its properties, very important, right? The properties of the bar magnet and also why the lines they do not intersect each other, correct? Magnetic field lines, why they do not intersect each other, 1 mark question. In today's class, we are going to learn one small derivation, that is expression for magnetic field at a point on the axis of the bar magnet. Magnetic field, expression for magnetic field at a point on axis of a bar magnet. On axis of bar magnet, or else this question can also be asked as magnetic field at a point on the axis of, show that magnetic field at a point on the axis of the bar magnet and a solenoid at a point on axis of bar magnet and a solenoid are identical. So anyway they can ask, either they can ask expression for magnetic field at a point on the axis of the bar magnet, or else they can also ask us show that the magnetic field at a point on the axis of the bar magnet and a solenoid are identical. See, this derivation is very important derivation, okay? So let us consider a solenoid. I have showed you the solenoid in our previous class. Now let me consider one of the solenoid. Okay, let me consider a solenoid. Okay, having n number of turns in it. Okay, it has having n number of turns. Out of that I have drawn any one. Okay, O be the center line. O be the center along the axis. Let the length of the solenoid be 2L. Okay, length of the solenoid be 2L and radius be A. A be the radius. Let P be a point at a distance, at some distance, let P be a point which is at a distance R from the center of the solenoid. P be a distance at a point, or P be a point at a distance R from the center of the solenoid. Okay, from the center. Now let us consider an element, one small element. One element we will consider of the thickness dx, which is at a distance x from the center. Okay, which is at a distance, any one we will consider. Okay, let us consider a circular element of the one of the element of the thickness dx, which is at a distance x from the center of the solenoid. So it consists of how many turns? N into dx, correct? If see here, n number of turns we said, so n into, for one the thickness is dx, so total it is n into dx. Fine. If let I be the current through the solenoid, let I be the current in the solenoid, then the magnetic field, magnitude of the magnetic field at a point P due to the circular elements is, so we have to find the magnetic field at a point P due to the circular elements of the solenoid. So how to find out? The magnetic field at the point P is, let us write it as dB is equal to, using Biot-Savart's law, we can write dB is equal to, correct, mu naught by 2, that expression what we have already got, mu naught by 2, n number of turns, correct, here, so see here, n number of turns, for thickness it is 1, so total number of turns is n into dx, so I can write n into dx, correct, n into dx, you can see those, no, fine, n into dx, I r square, correct, I r square by r square, here r is a, radius, I a square by r square minus x square, correct. Actually original formula is r square minus x square. So here our formula, what is the distance? This is the distance. So r minus x for one element. For one element we will do, so r minus x square, correct, r minus x square plus a square to the power 3 by 2. Because what is the formula we got? Using Biot-Savart's law in the derivation, B is equal to, or dB is equal to mu naught by 2, correct, I r square divided by r x square plus r square to the power 3 by 2. X square, x is now this much, that is r minus x. Or see the original formula. What was the original formula? dB is equal to mu naught by 2 I r square by x square plus r square, or r square plus x square to the power 3 by 2. If there are n number of turns, into n. See here what we have done. Let us consider a solenoid having n number of turns, and let us consider one element of the thickness dx. It consists of n into, correct, n into circular element of the, let us consider a circular element of the thickness dx. So write down, so while deriving this, initially you have to write, let us consider a solenoid of length 2L, area, radius a, with the center O. Let us consider a circular element of the thickness dx, which is at a distance x from the center. We have to find a magnitude of the we have to find the magnetic field at a point P, which is at a distance r from the center of the solenoid. So n into dx is the number of turns in that element, correct? N into dx is the number of turns. Number of turns. Then I be the current passing through the solenoid. Then the magnetic expression for magnetic field at a point P is dB is equal to mu naught by 2. For n number of turns, it is n into dx I a square, because r is here a, radius is a square divided by, for this distance you are calculating, that is r minus x. We get this distance. So therefore r minus x this square plus a square to the power 3 by 2. Understood till here? Next, we want the magnitude of the total magnetic field from here to here. Because of this, we want to find out the magnitude of the magnetic field at the point P, not because of one element. For total number of elements we want. So we have to integrate from x to from L minus L to plus L we want, correct? X is equal to minus L to x is equal to plus L, correct? Am I right? See, this is fully it is 2L, for half it is L. So we want to find the magnitude of the magnetic field from x is equal to minus L to x is equal to plus L. So let us integrate it. So how to integrate it? Integration of dB is equal to, correct? Integration of dB is equal to integration from minus L to plus L mu naught by 2 n dx I square divided by r minus x square plus a square to the power 3 by 2. Correct? Shall I raise this question so that it's easy for me to write? Okay. So integration of dB is b, correct? B is equal to mu naught by 2 is constant, correct? N I a square divided by what? Anything is constant here? Anything is constant here? Which I can take it outside? Yes. Which value? R minus x square plus a square to the power 3 by 2 is constant. This full term is constant. Only the varying is dx. So integration of minus L to plus L into dx. Correct, no? Mu naught value is constant. N number of turns, we know the number of turns, it will not change, so n is constant. What the amount of current we passing is also constant, so I is constant. Radius is constant, r is constant, the distance will not vary. So what and all is constant, we have taken it outside, only the varying is thickness. It changes, correct, for as the distance changes. So into dx. What is the total thickness now? Actually, what is the total thickness? It is, total length, it is 2L. So therefore I can write for this much the thickness is dx. For the entire solenoid the thickness is 2L. So therefore I can write mu naught by 2 n I a square. See here, what I want to say is this r is very very big compared to the x. Correct? So r minus x the whole square is approximately equal to r square. And if, so therefore I can write what? R square plus a square to the power 3 by 2 into entire d from L to minus L to plus L. What is the distance? 2L. So this value I can write it as 2L. Correct? Now look here. I will write over here. See here, why I got r, see here, why? Because, see here I will write, since r minus x whole square is approximately equal to r square. Why? Because r is greater than x. Since r is greater than x, we can write what? R minus x, the whole square is approximately equal to r square. Now, if suppose r is greater than a, if suppose r is also greater than a, then we can write, then what we can write? R square plus a square to the power 3 by 2 is approximately equal to r to the power cube. Correct? If r is greater than a, then r square plus a square to the power 3 by 2 is approximately equal to r cube. Therefore, we can write b is equal to mu naught n I a square divided by 2r cube. Correct? Into 2r cube. Let me multiply by, I forgot to write 2l, correct? Into 2l. Into 2l. Let me multiply and divide by pi. What do we get? So initially what we have done, we have considered a solenoid of length 2L having n number of turns. Let us consider a small element dx of thickness dx, which is at a distance x from the center of the solenoid. A be the radius of the solenoid. Let us consider a point P, which is at a distance r from the center of the solenoid, where we have to find the magnitude of the magnetic field. So the number of turns in the coil is, or in the circular element is n into dx. Therefore, using Biot-Savart's law, we can write Vb is equal to mu naught by 2 n dx I, number of turns, I a square by r minus x the whole square. Why it is r minus x? Because we want this thickness. So, r minus x will give you this small thickness. Therefore, we get, so r minus x square plus a square to the power 3 by 2. We want to find the magnitude of magnetic field from minus L to plus L. Therefore, integration of dB is equal to mu, integration from minus L to plus L, mu naught by 2 n dx I a square by r square, r minus x the whole square plus a square to the power 3 by 2. Next step is here. Integration of dB is b is equal to mu naught by 2 n, which and all is constant. We will keep it outside, which is not constant, we will keep it for integration, varying value. Okay, and I square r minus x square plus a square to the power 3 by 2 into integration from minus L to plus L, integration of dx. See here, r minus x, since r is greater than x, we can write r minus x square is approximately equal to r square. So therefore, mu naught by 2 n I a square by r square plus a square to the power 3 by 2 into 2l. If suppose r is greater than a, then we can write r square plus a square to the power 3 by 2 is approximately equal to r cube. So we get the expression. See here, integration of this one is nothing but for entire. So I have written 2l. Mu naught ni a square 2l divided by r cube. Let me multiply and divide it by pi. Then what do we get when we multiply and divide it by pi? We get the expression b is equal to mu naught n I a square 2 pi l divided by 2 pi r cube. Correct? What is the expression for the magnetic moment? M is equal to I a square. Correct? Sorry, I into a. Magnetic moment is equal to I into a. But for n number of turns, n I a. Correct? A is nothing but area. But what is the area here? 2 pi r square. R is nothing but a. So therefore I can write n number of turns, that is nothing but n. Correct? N number of turns. Therefore I can write n number of turns. So for how much length? 2l. So n into 2l is nothing but number of turns. For that element dx, total number of turns is dx into n. For 2l length, number of turns is 2l into n. Correct? N into 2l. Current is I. Area is nothing but pi a square. So this is the expression for the magnetic moment. You can see, no? Magnetic moment. So therefore we can write, where we have these expressions, there I can write m. See here, n I a square 2 pi l. So for this entire I can write it as m. Correct? Mu naught m by 2 pi r cube. This implies b is equal to mu naught m by 2 pi r cube. So b is equal to mu naught m by 2 pi r cube. Okay. Suppose we multiply and divide by 2. What do we get? what do we get? This implies we get B is equal to, suppose we multiply and divide it by 2, then we get B is equal to mu naught by 4 pi 2m by r cube. Correct? B is equal to mu naught by 4 pi into 2m by r cube. This is the expression we get for a solenoid, and this expression itself is same as the expression for the which is equal to the magnetic moment. Correct? Magnetic moment of a bar magnet is similar to the same as that of the solenoid. This expression says that even for the bar magnets, expression of the solenoid and bar magnets are identical. That is, B is equal to mu naught by 4.2m by r cube. The same expression is for the bar magnet also. Therefore, what we can say is this is similar or identical. Okay? Then, for Q, this charged body, we will speak that in terms of the pole strength, what it is, we will see now. Okay? So, learn this derivation, important. Suppose Qm is nothing but called as pole strength. North pole, south pole and all there now in magnet. So suppose Q is nothing but a pole strength, then of the bar magnet of length 2L, then can we write the expression for the magnetic moment as M is equal to Qm into 2L. Qm into 2L. If plus Qm is the pole strength of the north pole and minus Qm is the pole strength of the south pole, then also we can write magnetic moment is equal to Qm into 2L. This is one of the expression which you can use it for calculating the magnetic moment of the bar magnet which is having the pole strength Qm. Okay, for solving the problems in your JEE, NEET and also in theory it is important. M is equal to Qm into 2L. Or magnetic strength, pole strength Qm is equal to M by 2L. So please write one definition on your own. Pole strength is defined as the ratio of the magnetic moment to the length of the or dipole length. Magnetic moment, it is a ratio of the magnetic moment to the dipole length. Why we call dipole here? All the magnets, they have two poles, so we called it as a dipole length. So what is the SI unit? What we can write? SI unit of the pole strength? SI unit of the pole strength is ampere meter. Ampere meter, because M is equal to IA, correct? I is nothing but area, I is nothing but current. A is area, meter square divided by meter, M gets cancelled, so SI unit is ampere meter. Okay, so the expression for the magnetic field due to a pole strength is direct expression for you, expression for the pole strength. Using the expression of the pole strength, magnetic field is B is equal to mu naught by 4 pi 2 instead of M by R square. See here we can write M by R square is nothing but Q, correct? So we can write B is equal to mu naught by 4 pi Qm by R square. There is no derivation. E is equal to mu naught by 4 pi qm by r square is nothing but expression for the magnetic field in terms of the pole strength. Okay, this is one of the important expression for solving the problems. Next we are going to learn about the dipole in a uniform magnetic field in the next class. Please go through, okay, learn. These are the few of the important points in this. From this chapter, there is a possibility of asking many questions for your JEE and NEET. This chapter, current electricity chapter and all. Okay. Thank you.